Let's talk about reducing radical numbers. We're going to start with the square root. I want to remind you, when you take the square root of a number, you're always going to get a value greater than or equal to 0. We're still using the order of operations. I want you to think of the radical as being an exponent, and then anything under the radical is in parentheses. So my first one says the square root of 16. The square root of 16, I'm going to write this the long way, that 16 is 4 times 4. Since I have a pair of 4s, I know the square root of 4 is just 4. 64 is the same thing as 8 times 8, so the square root of 64 is 8. This next one's kind of interesting. I have the square root of negative 7 squared. Remember the order of operations. Before we take the square root, we would square negative 7. Negative 7 squared is 49. Then when I take the square root of 49, I think of 49 as being 7 times 7, which is just 7. So even though we see this negative under the square root, because of the order of operations, it becomes positive. Still looking at order of operations, I have negative the square root of 1. So we're going to hold on to that negative. I'm going to take the square root of 1, which is 1, so my overall answer is negative 1. So I can get a negative solution when I'm doing square roots, but it's because the negative outside of the radical was a multiplication of a negative number. When I have the square root of a fraction, I can think of the square root of the numerator over the square root of the denominator. The square root of 1 is 1, the square root of 16 is 4, so my overall answer is 1/4. I think the same thing when I get to the square root of 25 over 36. I take the square root of 25, and then I separately take the square root of 36. Square root of 25 is 5, square root of 36 is 6. So let's move on to the cube root. If I look at the cube root of x, I'm just going to get x. So it could be positive, it could be negative, it could be equal to 0. When I start with the cube root of 1, it is just equal to 1. When I look at the cube root of negative 1, it will be equal to negative 1. So I can see the sign of the number under the radical is equal to the sign of my solution. We're not always familiar with cube roots of numbers, and that's perfectly okay. It may help if you kind of break the number down that's underneath the radical. Let me show you what I mean. The cube root of 64, I could think, well, that's the cube root of, and maybe we think of 64 as being 8 times 8, and that's a good start. Then we can break that down further. So I say, well, 8 is really 4 times 2, and I have that twice, that's 4 times 2. But then let's go even farther, because we really are looking for sets of 3. So 4 is 2 times 2, and I still have my original 2. And then 4 again is 2 times 2, and then I have that trailing 2. Now when I look at groups of 3, I have 3 2's followed by 3 2's, which tells me 2 times 2 is 4. So the cube root of 64 is 4. So a very similar one, I have the cube root of negative 1 over 64. So I put that 64 in again. What I want you to see is we can separate the numerator, so the cube root of negative 1, and the denominator, cube root of 64. So we've previously said the cube root of negative 1 is 1, the cube root of 64 is 4, so my solution is negative 1 over 4. Let's do the same thing with the cube root of 8 over 27. I'll make that the cube root of 8 over the cube root of 27. Cube root of 8 is 2, cube root of 27 is 3, so my answer is 2 over 3. As we keep looking, things aren't always going to work out pretty, and we're going to have to break down numbers a lot. So I think it's nice to kind of look over perfect squares and just remind ourselves that these are the numbers we want to kind of extract out of our factors. So we know 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, 6 squared 36, right? These are numbers we're used to. And I listed all the numbers through 12 squares. So 7 squared 49, 8 squared 64, 9 squared 81, 10 squared 100, 11 squared 121, and then 12 squared is 144. As we look at these bigger numbers and we try to break them down, I want to try to break them down to squares if I can. And if I can't, that's all right. But these are kind of helpful as you're doing these radicals and trying to simplify. Let's take some examples to see what am I looking at. So I'm going to start with a small one. I have the square root of 8. And we've said, well, 8 we really think about is 4 times 2. So what we're going to do is separate the square root of 4 and the square root of 2. And we know the square root of 4 is 2, but the square root of 2 doesn't break down. So my answer is 2 square root of 2. We're going to start to see solutions that are simplified, but they still have a radical in them. When I look at the square root of 490, I see that 49 jumping at me. So when I separate it, I want to say this is 49 times 10. That way, when I have the square root of 49 times the square root of 10, I can make the square root of 49 7 and then keep the square root of 10. We're going to try the square root of 150. So when I look at it, I think about, well, what could possibly go into it? And maybe you're thinking 25 looks good because it's 50, so we could go with that route. So we could say 25. You could put this in your calculator and find out that 150 is 25 times 6. That's going to turn into the square root of 25 times the square root of 6, which is 5 square root of 6. So you can see I'm looking to bring out a perfect square. The next one says square root of 99. Hopefully the 9 really stands out, so when we separate it, we have 9 times 11. Square root of 9 times square root of 11 is 3 square root of 11. Remember that when I have a fraction, I can break this down into the square root of the numerator over the square root of the denominator. So the square root of 11 over 4 is the square root of 11 over the square root of 4. The square root of 11 does not simplify, but the square root of 4 does. It becomes 2. The next one says 5 times the square root of 135. The 5 outside I'm just going to hold on to, and I'm going to see what can I do to 135. Now, if nothing pops at you at first, why don't we take a 5 out? Because you can see 135 is divisible by 5. When you divide 5 into 135, you get 27. Well, let's break that down a little bit more. I can say that's 5 times the square root of 5 times 27 is 9 times 3. And what I want to grab here is this 9. So I keep the 5 outside. Let's take the square root of 9 and let's leave the 5 and the 3 together under the radical sign because they are not going to simplify. So I have 5, square root of 9 is 3, and then let's put the 5 and 3 back together on the radical to make it the square root of 15. So 5 times 3 is 15 times the square root of 15. I want to look at some other indexes, so let's start with the cube root of negative 24. Now that I've moved to a different index, I'm not looking at pairs, I'm looking to group by whatever the index is. And my index is 3, I want groups of 3. So we need to expand the negative 24. So let's say I wrote it as negative 6 times 4. That's a good start. Then let's keep expanding it. Maybe we say negative 6 looks like negative 2 times 3, and 4 looks like 2 times 2. So I'm looking at the index of 3 and thinking I need 3 numbers that are the same. So those 3 numbers that are the same can come out. So let's take out a 2. And then I have the cube root. Let's keep this negative, and I have a 3. So the 3 is a singular, the negative was a singular, so I kept them together. The only thing that's different that we're going to do is we're going to take this negative sign and we're going to bring it out front. So we're going to have negative 2 times the cube root of 3. Kind of looks prettier not to leave that negative underneath. These are equivalent, so it really is the same to do either way, but think of it kind of like punctuation for mathematics. Sometimes we have formats we like to use. The next one says I have the 4th root of 810. So let's write this as the 4th root, maybe of 81 times 10, because I think that's the factoring that really jumps at me. Then if I keep going, let's say the 4th root, let's say 81 is 9 times 9, 10 is 2 times 5, and then hopefully we see 9 as 3 times 3, and we get to write it twice. Then I still keep my 2 and my 5. So my index is 4, and I have 4 3s. That says a 3 comes out, I keep the 4th root, and then 2 times 5 is 10. So let's try 2 more. I have the cube root of 2000. So we go to expand it, we say the cube root of. So my first thought is let's break this into 20 times 100. Kind of take apart all the zeros. So I can see I had 3 zeros, I still have 3 zeros when I break this apart. So I'm going to write 20 as 2 times 10. I'm going to write 100 as 10 times 10. And then I see these 3 10s that match my index of 3. That says I bring 1 10 out, I keep the cube root of 2. My last one says the cube root of 16 over 20. So we're going to write the cube root of, and I'm going to expand the 16. I'm going to write 16 as 8 times 2, and then I just have a 20. Maybe you remember that the cube root of 8 is 2. If not, you can just keep going. You can say the cube root, 8 is 4 times 2, and then I have this 2 that we were multiplying before over 20, and then 4 can be 2 times 2, and then we have our other 2's, and it's all over 20. So we group the 3 2's, which says we take a 2 out in front of the radical, I keep the cube root of 2, and I'm over 20. What I want you to notice is this 2 out of the radical is even, and our denominator is also even. So we could cancel a 2, make it a 1, cancel with a 20. This makes it a 10. So I have this reduced, nice little radical, the cube root of 2 over 10. So all the rules that we've had and we've learned as we've talked about mathematics throughout the session, we apply as we get into radicals. So get to combine the simplification of radicals with the simplification of fractions.